Okay, let's take a look at how we take the concepts that we've learned so far about rotational velocity, rotational acceleration, rotational displacement, the rotational equivalent of force, which is a torque, and the rotational inertia, which is called the moment of inertia. So we've found the rotational analogs for all the things that we use to calculate how things move around, basically. Let's take all those things, put them together, and solve some dynamics problems. So the slides here walk you through the problem-solving approach. For this chapter, as for all the chapters that we've used, please follow these approaches. These are the ways that you will avoid making the mistakes of just sort of looking at the problem and thinking, well, gee, based on my everyday experience, this is what I think is going to happen, which unfortunately frequently leads you to the wrong conclusion. So I'm not going to work through these examples, and we're just going to do our own example. These provide you with a couple examples that you can work through. And this one here, they haven't worked through. Maybe we'll come back to that one, but I actually like a different example from the end of the chapter. And so we're going to do a rotational dynamics example. And before we do that, we're just going to cover a couple of points here about pulleys and ropes. And so the example problem that we're going to do involves a rope over a pulley. If we are saying that the rope doesn't slip on the pulley, in other words, the rope moves at the outer edge at exactly the same rate that the outer rim of the pulley is moving, then we can connect the motion of things tied to that rope to the motion of the pulley itself. And that's worked out in this final example from the slides, which has a bucket on a pulley sliding down. So we're just going to do actually a simpler example ourselves just to get us started here. Go through the slides. You can read those as well in your own time. I'm going to give you your own example here. So this is chapter 7, number 51. And in this example, there's a frictionless pulley modeled as a 0.8 kilogram solid cylinder with a radius of 0.3 meters. So let's draw the pulley, and there's a figure provided in the book for this problem. And there's its axis of rotation, is that dot. We are told that the radius is 0.30 meters, and we're told that the mass of the pulley is 0.80 kilograms, and we are told that the pulley is a solid cylinder. And the question is, there's a rope going over it, which I haven't drawn yet, which has people or something pulling on either end of that rope. And the question is, what is the angular acceleration of the pulley due to that rope? So I'm going to do something fancy here and use my ability to have colors to draw the rope. So there is a 12 Newton force on the left and a 10 Newton force on the right, and that's a rope, okay? So this thing here is a rope. There is no friction at the axis of the pulley. We were told it's a frictionless pulley. And we are told, actually we're not told explicitly, but the rope does not slip. And the question is, what is alpha of the pulley? What's its angular acceleration? Well, Newton's second law for rotational motion is that the torque equals I alpha. So that tells us that the angular acceleration is the torque divided by the moment of inertia. Well, the moment of inertia for a solid cylinder is equal to, and I'm going to have to go back in our notes to our table of moments of inertia. And for a solid cylinder here, we see in table 7.1 that the moment of inertia is 1/2 mr squared, where for this particular pulley, m is 0.80 kilograms and r is 0.30 meters. So we can plug and chug and get the number for I. That's great. That means the only thing missing to figure out the angular acceleration of this particular pulley is the torque. Well, how many torques are acting on this pulley? Pulley is affixed somehow to this particular central axis. So there are 2 torques exerted on it, one by each force. And because this is a rope, we know that the point at which the rope is pulling on the edge of that pulley there is where it loses its contact with it. And so at this point here, that's a right angle. Okay? And you can see that. That's a right angle there. And where this rope, where the rope on the other side leaves it, is also a right angle. If you've got a circular pulley and you drag the rope over it, it's always going to be having its last contact with the pulley at a right angle. So that means that each of those, the torque at each side is just due to, it's just the product of the force and the radius. I don't have to worry about cosine of phi or sine of any cosine or sine of any angle, because they're perpendicular to each other. So the first torque is the one, we'll just say, due to the 10 Newton force. So it's 10 newtons times 0.30 meters, r times f, times the sine of 90 degrees, which is 1. So that's 3 Newton meters. And is it positive or negative? If we were in the classroom, I would say, shout it out, right? Is it positive or negative? I use the right-hand rule, and that torque, this red 10 Newton force, would be trying to make that thing rotate clockwise, which is negative. So torque 1 is negative, and it's minus 3 Newton meters. Torque 2, the torque due to the 12 Newton force, is trying to make the thing rotate counterclockwise, so that's positive. So it's 12 newtons times 0.30 meters, which is 3.6 Newton meters positive. So the net torque is the sum of all the torques, and that's 3.6 minus 3, which is 0.6 Newton meters. So that's the net torque acting on this thing. So the angular acceleration is just that 0.6 Newton meters divided by 1/2 times 0.8 times 0.3 squared. That bit in the denominator there is the moment of inertia of that cylinder. So let's go ahead and see what that all works out to. 0.6 over 0.5 times 0.8 times 0.3 times 0.3, and we get 16.7 radians per second squared. And it's positive. That means it will be rotating in the counterclockwise direction. So that's an example. We'll do another example in a separate video.